Hello, my name is Dmitry, and I'm going to present you our work called Mobile Augmented Reality, Fast, Precise and Smooth Planar Object Tracking. Our work is focused on planar object tracking problem and its application in mobile augmented reality. The POT problem can be formulated as follows. Find the precise planar object position on a sequence of video frames using known object image. We propose a key point-based POT algorithm design that solves following 5 common POT problems. Poor performance under extreme perspective transformation and large-scale transformation, spatial jitter, degradation of optical flow tracking points number, and optical flow points drifting. We propose to combine optical flow tracking and image page descriptors into one robust tracking algorithm. In short, we call it OBD. The algorithm is split into two phases, detection and tracking. The detection phase is performed if the object was not detected in the previous frame. Detection is done by means of or binary descriptors detection and matching. Based on matched points, we compute pose and output homography transformation matrix, frame image, and detection result, whether an object was detected or not. The tracking phase is performed if the object was detected in the previous frame. For every frame in the tracking phase, the following steps are performed. First, using homography matrix, warp the current and previous frames so that the detected object is located in the center of a frame and is of the same size as that of the original object image. Second, using the homography matrix, project the object points to the current warped frame. Next, do sparse optical flow point tracking with warped previous frame and warped current frame as input images and projected object points as input points. After that, filter the tracked points using the descriptor matching-based approach and project matched frame points back to the current frame. Note that descriptor matching is slightly different from traditional descriptor matching, and you may find detailed description in our paper. And in the last step, compute the object pose using matched points. As output of each frame, we receive homography, frame image, and detection result, whether an object was detected or not. Therefore, by its design, OBD eliminates points drifting problem because OBD guarantees that the tracked points correspond to the same points on the template image. OBD eliminates optical flow points number degradation problem because number of input points for optical flow is always equal to the number of object points thanks to object points projection. Also, OBD provides smooth object pose transition between frames thanks to optical flow tracking algorithm. To evaluate OBD and compare it with the state-of-the-art POT algorithms, we use planar object tracking in the wild benchmark. The benchmark comprised of 210 video sequences with 30 planar objects and is considerably close to the generic mobile augmented reality scenario. Every object has separated video sequences of the following scenarios: scale change, rotation, perspective distortion, motion blur, occlusion, out-of-view scenario, and unconstrained scenario. As the evaluation metric, we use the alignment error. The alignment error is based on the 4 reference points object corners and is defined as the square root of the detected points and their reference ground truth, and can be calculated as following. Additionally, we evaluated spatial jitter of POT algorithms. We did it because the object pose detection by POT algorithms usually have small but visually noticeable differences between adjacent frames, even when the object and camera do not move, which results in 3D model shaking, or spatial jitter. And spatial jitter can be calculated as following. First, I will show you evaluation plots of the alignment error. Each plot shows the percentage of frames, vertical axis, whose alignment error is smaller than the alignment error value on the horizontal axis. On each plot, legend algorithms are sorted based on the representative score in the descending order. As the representative score, we use the alignment error with the threshold equals 7. As you can see, in the scale video sequences, OBD dramatically outperformed other trackers, and OBD successfully detected the object pose in 90% of the frames with alignment error equals to 7. In the perspective distortion video sequences, OBD also outperformed all other trackers and successfully detected the object pose in 79% of video frames with alignment error equals 7. Finally, OBD demonstrated the best average performance across all video sequences, and it successfully detected object for 82% frames with alignment error less than 20. And this is the plot of spatial jitter metric. The detection rate is the percentage of frames with alignment error smaller than 20. As you can see, OBD has the almost ideal post-transition across all video sequences with the highest detection rate. GPF tracker has almost the same spatial jitter, however, its detection rate is only 56%, and all other POT algorithms with low spatial jitter has detection rate below 30. Finally, OBD has small computational time and achieves 30 FPS on PC CPU, and using multithreading we also achieve 30 FPS on modern mobile phones with the resolution 720p. Additionally, in supplementary materials, we also provided video comparisons between our algorithm and Vuforia AR SDK. These videos clearly demonstrate that, at least for small target objects, Vuforia's algorithm has spatial jitter, while OBD doesn't have it at all. Thus, we experimentally show that the proposed tracking algorithm successfully solves the problems addressed in this study and offers state-of-the-art precision and delivers real-time mobile augmented reality with no spatial jitter.